Welcome everyone to section number 7. This is optimization problems, right? So optimizing stuff, that means we're going to find either minimums or maximums. This is our intro video, right? We'll get a little bit of practice in this, and then we have one more video where things will get a little bit more difficult. Our main objectives, right? Analyze real-world problems and transform these statements into mathematical equations. So that means we're going to get some story problems here. Then we want to apply all of our minima and maxima knowledge, right, to help solve these optimization problems, to actually find a minimum or a maximum. Okay, so again, this is going to be more of a story problem sort of section, and the claim is our last big story problem section was back in related rates. So in related rates, right, we tried to apply, really it was implicit differentiation here, implicit differentiation, to these story problems to figure out how these rates were related to one another. Now likewise, optimization problems, right, these are going to be story problems, and we're going to try to apply our knowledge of minimas and maximas. Right, we have the closed interval method, or we have first derivative tests and second derivative tests, things like this. We want to apply these to more story problems. Okay, so let's get to it. I want to show you an example, and then we're going to try to develop a technique to use on a lot of these problems. So we want to find the maximum area right there. I already see, whenever you see maximum or minimum in one of these story problem things, you should go to optimization, right? You're thinking now optimization, we want to maximize area. Okay, maximize area of a rectangle that's inscribed, aka right inside of, an equilateral triangle of side length 6. And we know that one of the sides of the rectangle lies along the base of the triangle. Whew, right? You may want to read that a second or even a third time to try to fully understand what is it talking about here. Once you've read it over a couple times, I recommend trying to draw a diagram, right? So I'm going to go ahead and draw. We have our equilateral triangle here. And we know the side lengths of this are 6. So 6, 6, and 6. And we know that we have inscribed inside of this thing a rectangle, right? So we have a rectangle, and I don't know exactly what it looks like. The only thing that I know is that the one side of the rectangle lies along the base of the triangle, so at the bottom here. So I'm going to go ahead and try to draw maybe something that looks like this. Okay, so here is a rectangle. It's inscribed in this equilateral triangle, and one of its sides is on the base of the triangle. Okay, but this doesn't have to be what it looks like, right? It could look like something like this. Or it could look something like this, right? There are lots of rectangles that you can inscribe, put inside of one of these triangles here. In fact, let me go ahead and color this in and really show where our rectangles are. So here is the first rectangle that I drew. Here is the second rectangle. And then finally I have the third rectangle, which is the longest one. Okay, and so again, the question comes down to which of these kind of rectangles that's stuck inside has the maximum area. So we want to maximize area of a rectangle. Well, okay, so now I know an equation for areas of rectangles, right? So area, for instance, is maybe width times height. Okay, that's something, but right, every time I've tried to maximize or minimize something even, right, from chapter 3, I've always had just one variable, right? When I go and try to find critical points and classify those critical points, I've always just had one variable, but now there's two variables. And so somehow I need to reduce that down, right? I need to get just hopefully one variable instead of having these two variables. So somehow I have to use this fact, right, that these rectangles are not just any old rectangles, but they're rectangles that are stuck inside of this triangle here, this triangle, equilateral triangle with side lengths 6. And so in order to do this, right, I maybe want to recognize that if I give you a specified width, right, the height seems to lie on this nice straight line. So maybe width and height are related to each other by a straight line, right? So for instance, if I was to give you, I said that the width of your rectangle was equal to 6, what does the height have to be equal to, right? And so if the width of your rectangle is 6, well, that means it has to be way down here at the very bottom, right? So it has to take up this entire length here and the height of your rectangle would be 0, right? There couldn't be any height to it because it needs to fit in this tiny corner right here. So the height would be equal to 0. Oftentimes in math, like, we write this in terms of a point, right? So you would say, if I give you 6, the output is 0, right? So again, width and height are related by some linear function here. So if you plug in 6, then you get out 0 into that linear function. Likewise, you could say, okay, if I gave you a width of 0, for instance, what would the height be equal to? So if I gave you a width of 0 for your rectangle, right, so you didn't have any width whatsoever, right, you would go all the way to the very tippy top of this triangle. Okay, so what is that height of this triangle in this case? Well, that's where we need to use a little bit of geometry. So let's go ahead and break up this triangle. We can see that we have a 6 here, refers to the 6 over here. Again, we're trying to figure out the height in this case of this nice right triangle. And in the bottom, this isn't going to be 6, but right, this triangle is being cut in half. So this is going to be 3. Now I can use my Pythagorean theorem to give us that 3 squared plus h squared is equal to the hypotenuse squared, 36. Subtract 9 from both sides, and now take the square root, and so I'm going to get root 27. Remember, this is a length of a side of a triangle, right? So it's going to be positive. Usually when we take the square root, we get a plus or a minus, but we're going to restrict down just to the positives. And now we can actually reduce this, right? You may want to go ahead and rewrite root 27 as maybe root 9 times root 3. And then root 9 is the same thing as 3. So you can write this as 3 root 3 if you'd like. So again, this is saying if your width is 0, then the height of that rectangle is going to be 3 root 3. Okay, now that I have these 2 points, right, we know a straight line is determined by 2 points. So let's go ahead and figure out the equation of that straight line that's relating together widths and heights. So usually for straight lines, you do something like y equals mx plus b. In this case, my independent variable, I'm giving you widths, right? So actually this x should be more like a w here. And then when I specify a width to you, the output is a height, right? So the dependent variable is a height. So instead of y equals mx plus b, I want h equals mw plus b, right? There we go. All right, now the first point that we got was if you plug in 6, then you get out 0. But actually I want to skip this for right now because actually this right here would be considered like the y-intercept. Let me show you what I'm talking about. So if I plug in 0, then I get 3 root 3. So the height is 3 root 3 when you plug in 0 everywhere you see a w. So notice 0 times anything is just 0. Oops, I forgot this is an equal sign right here. There we go. And so this gives you that your b value, right, that y-intercept, or really in this case it's more of an h-intercept, is 3 root 3. So now we can go ahead and write that in, right? So h is equal to mw plus b. And again, b was 3 root 3. Okay, so that was a nice point. Now let's go ahead and back up and use this. If you plug in 6, then you get out 0. So the height is 0 when you plug in, let's see, 6 for w. Now let's go ahead and solve for m. So negative 3 root 3 is equal to, I'll say 6m, divide by 6 on both sides, and I'm going to get that m is equal to, let's see, negative 3 root 3 over 2, once I've simplified down. Okay, so now that I have the m and the b value, this is telling us that the height, h, is equal to negative root 3 over 2 times w plus 3 root 3. So if you specify a w, this will give you out the corresponding height. Because again, the fact is that this rectangle, it's inscribed, it's trapped inside of this equilateral triangle. Okay, so now that we have this nice equation that somehow relates together our widths and our heights, let's go ahead and use that to get this in terms of just one variable, right? Again, we're trying to maximize area of the rectangle. W is fine, but height, let's go ahead and replace that. Again, our equation is negative root 3 over 2 times w, negative root 3 over 2 times w plus 3 root 3. And now we have an area equation with just one variable. So now I can actually take the derivative of this thing, find critical points, all that good stuff that I love to do, right? But I couldn't because, again, I had two variables. So somehow I need to restrict down to just one variable. Okay, so if I want to take the derivative of this, actually maybe even before I get to the derivative stuff, let's think a little bit about domain, right? What are the allowable values for w? Now that I have just this one variable, I want to specify what is the domain of this thing. Well, widths of rectangles, right, those should be positive, or at least worst case maybe 0. So at very worst case, 0 should be the smallest width I can have. I certainly don't want negatives. And then the biggest width, well, remember, we're stuck inside of this triangle, and this triangle has a width of 6, right? Its base is width 6. And so if you want to say stuck inside of that triangle, as we do in this problem, right, the maximum width should be 6. Okay, so that is the domain, right? That's where we're going to be searching for critical points between 0 and 6. So let's go ahead and take the derivative, or actually even before I take the derivative here, let me distribute, right? Because as it sits right now, if I wanted to take the derivative, I'd have to use the product rule, and that's annoying, right? So if I distribute, I would get negative root 3 over 2 times w squared plus 3 root 3 times w. Now I can take the derivative and I don't have to use any rules, right? Any product or quotient rules, things like that. So if I take the derivative, I'll get negative root 3 times w plus 3 root 3. And now I'm searching for critical points. So I'm looking for where is this undefined, or when is it equal to 0? And well, it's never going to be undefined, no matter which w value you choose, right? There's no division, there's no square roots with a variable inside them, things like this. So the only hope for critical points are when the derivative is equal to 0. So let's see, set that equal to 0. Now let's go ahead and solve. So negative, oops, I'm going to add that to both sides. So positive root 3 times w is equal to 3 root 3. Let's divide through by root 3 on both sides, and we get that w is equal to 3. So that is a critical point, and I'd love for that to be a maximum, but I'm not sure yet, right? Because critical points, they can be maximums, they can be minimums, they can be boring critical points. There are critical points out there that are neither minimums nor maximums. And so we have to check, right? We have to show that 3 is actually the maximum. And so in order to show something is the maximum, right, we have a few options, right? We could use the first derivative test or second derivative test to show that it's a maximum. Or in this case, because we're on a nice closed interval, right, we can actually use our section 1 stuff, right, the closed interval method. So that's what I'm going to do in this case. So, right, the closed interval method says you should check at the endpoints and at your critical points, and then whichever one is the maximum of those 3, well, that's going to be the absolute maximum on that interval. So in this case, I need to check at our endpoints, 0 and at 6, and then at our critical points, at 3 in this case. And whichever one of these is the largest will be the absolute maximum. Okay, so if I plug in 0 to for width for our area function, so up here, here's our area function right here. If I plug in 0, well, I'm going to have 0 times, well, who cares, right? Because 0 times anything is 0. All right, so that's not the maximum. At least I hope not. If I plug in 6, well, if I plug in 6 here, notice what happens, right? So I have this 6 divided by 2, that's going to be 3 in this case. And I have a negative 3 root 3 and a positive 3 root 3. So those are perfectly going to cancel out and give out 0 for this part. And again, so we have 6 times 0 is going to be 0. And that kind of makes sense, right? Because that height, we know, oops, one more up. When you plug in 6 for your width, you get out a height of 0. So that's why this had to be 0 right here. So again, when you plug in 6, you get out 6 times 0, which is 0. All right, so our only hope is actually at 3 here. So if I plug in 3, now everywhere I see a w. Let's see, I'm going to have 3 times negative root 3 over 2 times, again, I'm plugging in 3 everywhere I see a w, plus 3 root 3. All right, so maybe let's go ahead and factor some stuff out. I noticed that all of these terms, they have a 3 and a root 3, so let's go ahead and factor those out. So I have this 3 out here, and then I'm going to factor out another 3 and a root 3. And when I do that, let's see, I'm going to have negative 1/2 left in the first term. And in the second term, well, I factored out the 3 and the root 3, so all I have left is 1. So, okay, so now negative 1/2 plus 1, so that's just going to be 1/2 in this case. I can also start combining stuff out here, right? 9 root 3 times our 1/2, or we can finally simplify this down to 9 root 3 over 2. Okay, so that's the biggest one. So this is going to be the absolute max. Now we have to make sure that we are answering the question that was given to us. So in this case, it asks find the maximum area. So it doesn't say find the dimensions of the rectangle that give maximum area or anything like this. It wants what is the maximum area. So in this case, the maximum area is 9 root 3 over 2. And you should go back and you should search for units, right? Is this centimeters? Is this inches? In this case, it doesn't have any units specified. So let me go ahead and I'm just going to, kind of getting us into a good habit here. I'm just going to say units. And because this is area, right, so it should be kind of square units. There we go. So there is our maximum area. Okay. So that is the first problem. You can see that these are tough problems, right? These story problems are indeed, they're challenging. They take a little bit. But I want to give us kind of a general strategy that we can apply to kind of all of these types of problems, hopefully. So here it is, this theorem 7.3, steps for solving optimization problems. So the first thing that you want to try to do is, of course, understand the problem. So we read it one time through. I recommended that you read it twice or even 3 times through, right? You want to determine what is given and what is unknown for these problems, right? We want to maximize area in that case. The second thing that we did was draw a diagram. Now you don't need to necessarily draw a diagram for every single problem, but you'll find in a lot of cases this is useful. The next thing is that we introduced notation. So kind of going along here, we drew our diagram, then we introduced notation, right? I decided to use W's and H's, but maybe you wanted to use length times width, or maybe you wanted to use X's and Y's, right? But you have to introduce some notation so that we can actually do math with it, right? So that's our third step. Introduce notation, assign symbols of what needs to be maximized or minimized, select symbols for other quantities, and label the diagram when appropriate. Next up, we wanted to find an equation that relates the quantities with what needs to be maximized or minimized. So that's, in this case, right, we wanted to minimize or maximize area. So this was our step 4 right here. Find that equation that relates these quantities, these widths and these heights, with what needs to be minimized or maximized. The next step is that we had too many variables here, so, right? So we wanted to use restricting equations. In this case it was just one, but sometimes there can be multiples. Restricting equations to reduce down to just one variable, right? So we held off on taking the derivative of this thing because we said, well, there's too many variables. We want just one variable. So we spent a lot of time here trying to figure out how are the widths and the heights related to each other, right? So that we could restrict down and just have one variable. And then finally, once we have that equation for area in this case, in terms of just one variable, then we're going to use methods in 3.1 or 3.3 to find absolute minimums or maximums, right? So that's going to be either the closed interval method, or we can use, right, the first derivative test in some cases. So that was like 3.3. Okay, so just like in related rates, you'll kind of feel that a lot of these problems, they're quite different from each other, right? The setup and all that sort of stuff, we're going to use different, we could use volumes and all that sort of stuff to relate these things together to try to optimize or maximize or minimize. We want to maybe minimize cost or maximize profit, all these sorts of things. And so they will sometimes feel very different. But this right here is kind of a strategy that does work for all of them. Though I admit, I mean, this is definitely a broad strategy, right? So let's go ahead and try doing this for one more problem before we end this video. The sum of two positive numbers is 16. What is the smallest possible value for the sum of the squares? So smallest right here, smallest is that we want to minimize. So we want to minimize the sum of their squares. Okay, so the thing that we're trying to minimize, again, is some function here. Maybe I'll do f. And that function is, we're going to square them, and then we're going to sum those numbers together. So maybe these two positive numbers, I'm going to call them x and y. So x and y, positive numbers. Positive number is a positive number. Okay. So the thing that I want to minimize in this case is the sum of their squares. So if you square them, and then you sum those together, this is the thing that I want to find the minimum of. Okay, well now, notice in this case, maybe it doesn't necessarily make sense to draw a diagram, right? But still, you're understanding the problem. We've introduced notation. Now we want to find an equation that relates together the quantities that we have with what needs to be solved. So in this case, we did that. F is equal to x squared plus y squared. And now we want to find restricting equations, right? Because again, there's two variables here. I don't know how to find the minimum or maximum of something with two variables. So we need to restrict down to just one variable. So that's where we're going to use this fact back here. The sum of these two positive numbers is 16. So if I was to just take the regular old sum, we would get 16. So now we can go ahead and maybe solve for just y or for just x. So I'm going to solve y equals 16 minus x. So this is a way to relate together the x's and the y's. So now let's go ahead and plug that in and use that restricting equation to get this in just terms of one variable. So instead of y, I'm going to put 16 minus x, quantity squared. Okay, again, maybe before we start taking derivatives, let's remind ourselves, what should the domain of this function be? So in this case, x is a positive number. That's the only thing that we have. So in this case, x should be greater than 0. We do know, however, that when you sum these things together, right, you should get 16, right? So there is a bound on this, right? So x can't be 100, for instance, right? Because y is also a positive number. So if x is 100, y has to be positive. There's no way you're going to get back down to 16, right? So this is saying that the maximum that x can be is actually, something very, very close to 16. It can't be quite equal to 16, right? Because again, y also has to be a positive number. So x is somewhere between 0 and 16. Now let's go ahead and find the minimum of this function here, the sum of their squares. So we're going to take the derivative and look for critical points. So this is going to be 2x plus 2 times 16 minus x. Don't forget about our chain rule, right? So this is derivative of the outside, leave the inside alone, times the derivative of the inside. So we have to multiply by -1 there. And we're searching for critical points, right? So we want to know, when is this undefined, or when is it equal to 0? Well, it's never undefined, right? There's no division, there's no square roots. So our only hope for critical numbers are when this is equal to 0. So now let's go ahead and maybe also distribute this a little bit. So 2 times 16 will be 32. 2 times -x will be -2x. And oops, I forgot to distribute this negative sign as well. It should also distribute. So this is actually going to be -32 and +2x. Okay, let's go ahead and rearrange and try to solve. So I have 32 is equal to 4x. So that's going to give us x is equal to 8. All right, so x equals 8 is a critical point. Again, I don't know that this is where it actually minimizes, right? So I want to show that it actually minimizes here. So in order to do that, well, notice we don't have a closed interval in this case. So I'm going to go ahead and use the first derivative test. So first derivative test, let me go ahead and draw out my number line. This is going to be just from 0 to 16. And here we're breaking up our number line at 8. That's our critical point there. We're going to choose some test values. So maybe I'm going to choose something like 1, and I don't know, I like 10. Why not? So I'll plug in 1 and 10 as my test points, and I want to know, is the derivative positive or negative, right? Because that'll tell me if the function's increasing or decreasing at these points. So again, here's maybe my derivative function right here. So if I plug in the value 1, right? So if I plug in 1, I'm going to get 2 minus 32 plus 2. Well, that's going to certainly be negative. So in this case, the function is decreasing on the interval from 0 to 8. Now how about if I chose like 10 and I plugged it in? So if I chose 10, I would have 20 minus 32 plus 20. So that's going to be 40 minus 32. That's going to be 8. But the big thing here is that it's positive. So it switches from negative to positive. That is decreasing, right? The derivative is negative, so the function's decreasing, to positive, the function's increasing. So therefore, at 8, we actually do have a minimum. So we have x equals 8 is a minimum. And in fact, in this case, because there's only this one critical point on our domain, we know it's actually an absolute minimum, right? So over here it's bigger and it's decreasing, 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 and we get down to a minimum here, and then we increase, 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 and then we stop. So this actually is the absolute minimum. All right, so x equals 8 is the absolute minimum. Let's go ahead back up here. What does it want, right? It wants what is the smallest possible value for the sum of the squares. So in this case, I have an x value, but it wants to know what is the smallest possible value for the sum of the squares. So in this case, I want to figure out the f value. So let's go ahead and plug in 8 into our f. So in this case, f would be equal to 8 squared plus 16 minus 8 squared. So that's going to give me, well, this is also going to be 8 squared. So 8 squared is 64 plus another 64. That's going to be 128. And so the smallest value for the sum of the squares is going to be 128. And again, you can check for units and stuff. In this case, there really aren't any. All right, that is it for this video. We've seen 2 optimization problems, one a maximum, one a minimum, and you can see how these are very different, right? So we need more practice. That's where our next video is going to come into play. I'll see you guys then.